problem. A 4-gram ping pong ball is attached by a thread to the bottom of a beaker. When the beaker is filled with water so that the ball is totally submerged, the tension in the thread is 2.8 times 10 to the negative 2 newtons. Determine the diameter of the ball. Okay, so a beaker. A ping pong ball is a really light air-filled ball. So similar to a beach ball, if I were to just throw it into water, it would float on the surface. In this case, we've taken the ball and attached it using a thread, so a really light string, to the bottom of a beaker. And then we filled the beaker with water so that the ball is totally submerged. What that means is when we talk about our buoyancy equation, the Vn is going to be the V of the ball as a whole. V of the object, V sub O. So the entire ball is submerged. They're telling us that this force of tension is 2.8 times 10 to the negative 2 newtons. They've given us the mass of the ball, so 0.004 kilograms. Let's go ahead and draw our free body diagram. So the ball itself, the thread is attaching the ball to the bottom of the beaker. So the string, this thread, is pulling downwards on the ball. There is, of course, a buoyancy force, which is always upwards because it's always opposing gravity. And then the ball itself has the force of gravity acting on it. So mg. So 3 forces acting on this ball. The buoyancy force upwards, the force of gravity downwards, and the force of tension downwards. Since this ball is no longer moving, it's just now in the water, its tendency would be to pop out of the water, but this thread, this little string, is not allowing that to happen. So the net force on this ball is 0. So we can say that buoyancy force upwards has to equal the tension force and mg downwards. We've been given the force of tension, we know the mass, so we can totally find mg as well. So we have enough information to find this buoyancy force. But let's go ahead as well and substitute in the buoyancy force. The basic equation is that buoyancy force is equal to the density of the fluid, the volume in, so the volume displaced, which actually is just going to be the volume of the ball this time because the ball is completely submerged. So Newton's second law allows us to relate these 3 forces, the buoyant force upwards, the tension and gravity downwards. And we actually have everything except for the V, the volume of this ball. And so we can calculate for that. Don't try to cancel out G, by the way, because it's not in every term. So our tension force, 2.8 times 10 to the negative 2. That's already in newtons. That's what we need. The mass, we've converted to kilograms. So when we multiply by 9.8, that's in newtons as well. This beaker is filled with water, so we just want the density of water again, which we get off the test notes. let's see here. 2.8. 2. Let's put my calculator in scientific mode so I don't have to count my decimal places. 6.857 times 10 to the negative 6. My units on this will be meters cubed. So again, in the numerator, we have newtons. In the denominator, we have kilograms per meter cubed times meters per second squared, which this portion is a newton. So the newtons cancel. 1 over meters cubed becomes meters cubed. I might have said meters squared. Sorry about that. So meters cubed is our volume. Now, to finish this out, the problem is asking us to find the diameter of the ball. Well, it's a ball, it's a sphere. We know the volume of a sphere, or if we don't remember, it's actually on the back page of the test notes as well. So, looking at the back page of the test notes, the volume of a sphere is 4/3 pi r cubed, where r is the radius. So we will be able to solve for r. I'm taking this to the 1/3 power, since I haven't taken the time to figure out my cubed root button. So 3v over 4 pi to the 1/3 power. I'm getting 1.18 times 10 to the negative 2. This will be in meters. So we could essentially say 1.2 centimeters. But the problem's asking for diameter, which of course we just need to multiply by 2. So 2.4 centimeters. And leaving it as 2.4 times 10 to the negative 2 meters is fine as well. So buoyant forces, this is going to be a bit of a review to back when we were talking forces and Newton's laws. We just have a new fundamental equation that describes the force of buoyancy. And then we also need to think about Newton's second law in terms of the net force acting on the object we're talking about.